Z over yx times y over z, which is 1 over x. So what's f xx? Okay, what's f xxx? Right. I think what you're going to find is that the sort of like dn of f dx to the n turns out to be something like -1 to the n -1 to the n minus 1 factorial over x to the n. Some pattern like this is what falls out of this when you do it now. Oh, it's even easier. I mean, yeah, here I am doing it that way. When instead I could have written as the log of x plus the log of z, and I do no algebra at all. Nice observation. I like doing it the hard way, I guess. Yeah, this makes it even easier because then you just throw away everything except whichever variable you're working in at any given point, right? And the pattern will be the same for all of them except with an extra -1 in the z case. Yep.
I'm sorry. Going back to the is that just Jacobian matrix like A transpose times that second derivative matrix times A?
Yeah. Yeah. Yep. As an operator, then all applied to f out here, basically. Yep.
On 21 of the second part.
Yep.
With the specific question you asked about using 3.8 to find the approximation. Get that one.
All right. Okay, so let me pull it up real quick so I have it in front of me. So that one was, okay, so using definition 3.8, calculate a linear approximation from the function in 2.521. Okay, so 2.521 is y e to the x. Okay, so you have y, it's f of x and y is equal to y e to the x and g of s is s minus ts plus t. And we're going to be considering f composed with g of s and t is what we're after, right? So the idea is that we want to try to write down the equation of a tangent plane to this thing, right? And I think I gave you the specific point. Which point did I pick? 1, for s and t. Okay, so what do I need to do to compute a tangent plane? I mean, this is just, even if I plug g and s and t into this, this is still just some z value, right? You put in s and t and a z comes out. So this is some z value. So it's a surface. And you can compute a tangent plane to that surface. So the formula for the derivative says that a tangent plane has the form x h of s and t should be equal to f of s naught t naught plus d, and then we're going to write f composed with g of s and t. Because we're either going to plug the s and t in and compute the derivative, or we're going to compute the chain rule, right? Times, I guess x s. The best way to write this. I would call it. Let's do it this way: s minus s naught, t minus t naught is a vector. Yeah.
You mean to put f of s and t naught, that's not t naught, or
F composed with G. F composed with G. The thing is, this is kind of artificial because we can think about F composed with G as taking variables S and T, or just that being F if we do the composition. But the idea here is that when you compute these, is this the definition, or we use the gradient definition here? It must have been this one.
Yeah.
Right. Okay. So this is just a typical, like, how do I compute a derivative of a function like this? I have a point where the function starts. I've got some object that's controlling the slope, and then I have some vector that controls where my points are at, right? A vector that keeps track of, in fact, I think in this setup, it looks like this. Whether for the matrix multiplication to work correctly. I think it's a column vector. Okay, so really the only question here is, oh, and this is also S not T. The question is, what's this? The D of F composed with G of S and T is supposed to be equal to dF in its original variables times dG in S and T. The only possible thing we got to worry about here is this computation, right? In this problem. If I want to compute a derivative for the tangent plane of a, for the sort of direction of a tangent plane, I need to know what this is. So I'm just going to compute those things. What's dF? Well, it's the matrix that has fx in the first coordinate and fy in the second. There's dF in x and y. What's dg? Remember, D's got two components, right? A first component and a second component here. So I'm going to do the first component with respect to x, the first component with respect to t, the second component with respect to s, the second component with respect to t. If you did this and only got one row out, you know you'd be wrong here because your matrix multiplication wouldn't make any sense, right? You'd have like a 2 by 1 times a 2 by 2, which you can't do. Where am I going to get x and y values to plug into df? I mean, dg is just constant, so that's easy. Where am I going to get x's and y's? If only I had a relationship between the 1, 1 that are s and t values and the x's and y's that I need to plug up in here. Oh, look, there it is right there. So g of 1, 1 is equal to 1 minus 1, 1 plus 1, which is 0, 2. This is the x naught and y naught values that get plugged into the second function, right? This is the x and y that gets thrown into the f. So if you want to know what this is, df at 0, 2 is equal to 2, 1. So the x and y value that we fed into f were the values that g spit out. G is giving us the x and y coordinates. That's what the first and second component of g do. So now, what's the equation of the thing in the end? Well, what's f of 0, 2? F of 0, 2 is equal to 2. So h of s and t is 2. That's the value of the function at s is equal to 1 and t is equal to 1. Plus this matrix multiplication, 2, 1 times 1 minus 1, 1, 1 times the vector that makes this make sense. I mean, this is what, 1 by 2, and this is 2 by 2, so you get a row vector out the other side. So if you put a column vector here, you're just going to get a single number out the end, which is what you want, right? So s minus 1, 2 minus 1. And I wouldn't take it any further than that. I would leave it. If you want to multiply it out, you can. But this is an appropriate linear approximation for this function at this point. And you would have gotten the same thing if you'd actually composed these functions and just computed the derivative directly as well. Right? The idea is that you don't need to do that if you don't want to. So I asked the question because I'm trying to drive home the point that in practice, what these things are used for is these sorts of linear approximations. So I hope that clarified what I was after. Yep.
We talk about exercise 34.
34. So 34 is seen on the surface. 34 looks like the exercise for 31, but it's different because it's actually asking you to show that something is a solution to yeah, I mean, do you guys know what implicit differentiation is? That's a good question, actually. So the whole reason I put this on here was to ask you, do you remember what implicit derivatives are? Okay, I'm going to remind all the some people are like, yeah, I totally like, please don't show us implicit differentiation again. Everybody else is looking at me like, oh my God, please don't show us implicit differentiation. But that means I have to show it to you anyway. So I'm going to write down an equation for a function that is implicitly defined, right? So y is going to be an implicit function of x. And what that means is I have an equation where I have not solved for y. I have not solved for y, right? This describes some curve of points that exist in the xy plane. There's a bunch of solutions to it, but it's not a function where I have y on one side and a bunch of stuff in x on the other. The x's and y's are all mixed together sort of inextricably because of this cosine y and this squared y here. There's no way to get y by itself. So this is what's called an implicit function. And sort of an alarming number of ideas in the sciences come in the form of implicit functions. So one thing you can do with these is, even if you don't have the function y equals f of x, you can still compute the derivative of this. And the way you do it is, you use the product rule, because everywhere you see a y, that's really a y of x. Y is a function of x. And so the derivative of any y that you see is dy dx. Y is a function, right? So if you're going to compute an implicit derivative, I promise this has a point right there. Implicit derivatives are super important because they let you get the idea of slopes without actually knowing what the functions are. You can all, and this is actually the way they did this in the old days, and the computers do it. They would find some point that was a solution to that thing, and then they would compute the derivative, and they slide a little bit in that direction using something called Euler's method, if you've seen it. Then, after you've gone in the direction of the derivative, you calculate another derivative at that point, and then you go in that direction for a while. And what you end up describing is a sort of a numerical approximation of the paths that those functions can follow. Okay. So the way that you compute a derivative is just do it. D by dx of xy squared plus x cosine y is equal to d by dx of 0. Well, that's easy. And on this side, y is a function of x, and so you have to treat it like one. So you use a product rule here. X times a function of x should be 1 times y squared plus x times the derivative of y squared, which is 2y dy dx by the chain rule. The chain rule says the derivative of y squared, because y is a function, is the 2 comes down, leave the y alone, then multiply by the derivative of y, which is y prime. Hopefully I'm bringing some bells here about the way this works, right? Ultimately, what we're going to do is we're going to get a pile of dy dx's we're going to solve for. So if you keep going with this, cosine y plus, minus x sine y dy dx is equal to 0, again by the chain rule. So you product rule here, use the chain rule here. You should notice that what you end up with in the end is, so the trick I guess is 2xy, that's inside of the dy dx, and then you also have a minus x sine y. Now I know I'm probably reminding people because this algebra is the most annoying part of all these things. Minus y squared minus cosine y. And so the derivative dy dx as an implicit function is given by minus y squared minus cosine y over 2xy minus x sine y. Every one of you should have seen this at some point in the past, right? Like somewhere in like the calculus sequence, you did these things.
Did you make this equation up just now? No, it's not in 34.
I just made it up. 34 is the general description of what's happening, but I'm going to use this equation to show you what's going on in 34. What is this? So this is the way we did it. When you do this in calculus, you do this long-winded approach right here, right? Every single time you do these questions, you do this long-winded approach. But notice, I could rewrite this as minus y squared plus the cosine of y. Does that look like a quantity that arises from this derivative somewhere? Like if I just wrote this function down right here, like that, it has to take some derivative of it. Does this thing result? It's the partial derivative of that function with respect to x. So this is minus fx. And in the denominator, 2xy minus x sine y, that looks an awful lot like 2xy minus sine x. That looks like fy. So when you're done with this computation, what you realize is the entire time that they taught you how to do implicit functions, there was a formula for it. All that algebra, all those hours of grinding out implicit derivatives, and instead, if from the beginning, you had said, call this function f of x and y, then dy dx is equal to minus fy over fx. That's the formula for implicit differentiation. then you can just derive that. So the point of 34 is to show this directly. It's not an accident it does this. The point of 34 is that this holds. Yep. Yeah, I got it upside down. That's the point of this computation, is to show that. Right, that working symbolically, you can actually prove that this holds. If you have a function that is defined in terms of x and y, this just holds. I mean, okay, you want to know the engineer's proof of this? Multiply both sides by dx and multiply both sides by fy, and then partial integration, and you'll get f back on both sides. So it must have been true when we started. Oh, yes. Okay. Everyone here's done differential equations at some point. Somebody, whether or not you did it willingly, somebody taught you differential equations. Okay. So one of the things you guys learned when you did differential equations, when you were studying things like exact equations, you had exact forms, right? Exact differentials. You did partial integrations where you had a function of two variables that you integrated with respect to just one of them. And instead of just having a constant show up, you had a constant that was a function of the other variable show up, right? So yes, absolutely, it's the case that partial derivatives have an inverse operation called partial integration. And that's the basic idea of an approach like this, is to use partial integration. Okay, so I haven't concretely answered your question, but I'm trying to give you an idea of what is going on in the background. So work on it a little bit more. We got another day to talk about this. Okay. So let's talk about glue stuff for a bit. Okay. So we've been studying functions of this form. F takes x in Rn into R. This is kind of what we've been working on, right? Surfaces are what we've been studying. So we're going to sort of flip gears and we're going to study two different kinds of functions now, functions of enormous physical importance. We can think about these as, these belong to a family called scalar fields or surfaces. So we have two new objects that we're going to look at that are central objects, that's sort of central mathematical objects. The first is a family of things called a path. So a path is a function that takes an interval in R and spits it out into Rn. Okay, so you can imagine if you have a one-dimensional input, what's happening here is you get this twisted path sitting inside of n-dimensional space. So as an example of a path, you can think about f of t is equal to 2 cosine t, 2 sine t, t. This is a helix, right? There's no surface here. Nothing is connected because this function spits out a one-dimensional image because the input was one-dimensional, but it takes in one variable and spits out some curve. So paths, this particular path goes like this, which is why it's called a helix. So it twists in these two variables and increases in this one. Right? The z is going up constantly, but the x and y are rotating on this circle, cosine and sine. The other thing we're going to be looking at are things called vector fields. Those will come second. So a vector field is an F that takes a domain in R. Usually we're going to think about it as being R2 or R3, but from R3 into R3. Specifically, these vector fields get used because in R3 there's a cross product. So most of the vector fields we'll be looking at will be in R3. Okay. But these are two new families of functions. We will not be able to use some of the ideas that we developed about surfaces because it doesn't make any sense to talk about a tangent plane of one of these guys. And the first object that we want to talk about is the path. First, we'll talk about 3.1, which is differentiable paths. This is just a sort of general survey. Have any of you seen any proof at all that Kepler's laws hold in any class? One? Okay. Do you know what Kepler's laws are? So Kepler's laws are the laws that describe planetary motion. So Kepler, on the basis of, sort of the invention of calculus was predicated by this discovery. So an astronomer by the name of Tycho Brahe set up a huge telescope where he recorded the movements of the stars for decades, like endless pages of just numbers. And what Kepler did, by looking at those numbers, Kepler figured out that the things in the sky that were moving like planets were traveling elliptical paths. Right? He sort of parameterized what was happening and said the only way this makes sense that we're seeing this observation is that what we're looking at is an elliptical path. And so he formulated 3 laws of planetary motion in response to what he saw in this data. And then Newton and Leibniz and the Bernoulli brothers actually made it rigorous. So they actually, calculus was partly invented to make it rigorous, to tie together. Kepler didn't know that gravity existed. So from the basis of nothing, he basically said, these numbers I'm seeing are ellipses. And he formulated 3 laws of motion. And it wasn't until Newton and Leibniz invented calculus that Bernoulli could come along and actually make it concrete. Oh, the theory of gravity actually is why the stuff is actually, once you know gravity exists, you can prove that the planets travel on elliptical paths. Okay? So this is one of the grand accomplishments of vector calculus. And one of the things, at least I want to show you the derivation of the first law, because it's actually really straightforward once you know something about the way vectors work. And we're going to require a couple of facts about paths to get there. So the first is, we're going to talk about always a differentiable path. So a differentiable path is a function x that takes some interval I contained in R into Rn. For our specific case, we're going to be talking about paths in R3, but a differential path is a function x with x prime of t exists. So the derivative of the function exists. And because this exists, we can call it, what's the derivative of position? Velocity, sweet. V of t. It's called the velocity. So if we have differentiable paths, then we have a notion of velocity. And we want that because we want to be, velocity is going to help us keep track of how a path is turning in space. So I here is an interval. I is an interval. By I mean anything of the form AB or AB or A infinity or what have you, right? It could be infinity to infinity. The point is, whatever I is, it has to be an interval, right? I want to have a path have sort of a notion of motion from the earlier to later, and so I have to have intervals. I don't want to have them jump in space. If V is differentiable, then V prime, probably not surprising, derivative of velocity. So you guys well brainwashed by your years in physics classes, right? So the derivative of position is velocity, and the derivative of velocity is acceleration. One notational convention that we use here is these are vector quantities. Position, velocity, and acceleration are vector quantities. When I want to refer to their magnitudes, I will use a letter without the hat on it. I will try. In the book, she uses bold letters and not bold letters. If I say V without a hat, what I mean is the length of V, which is the speed function. So V is the magnitude of the V vector. So that's speed. It's still a function of t. In all cases, we're going to be assuming these aren't constant. Things move in calculus. Okay. So one of the first things that we learn about paths is that I can, if I have a differentiable path, I can always find a tangent line for it. The way I do it is like this. It's a theorem, kind of not very complicated theorem. It's not even a theorem, it's called definition. If X is differentiable and V of T naught is not equal to the zero vector. So all of these mechanics break down when things stop moving. Right, so we're not going to allow velocity to ever be the zero vector. If f of x is differentiable and the velocity vector is never zero, then the tangent line to x at the vector v naught is L of t is equal to v naught plus x prime of t naught times t minus t naught. We've done this over and over again, right? Here we go. Look at it. Once again, it's slope-intercept form. Vector slope-intercept. This is a parametric equation for the tangent line. This is the point on the curve. Actually, so b naught here is, we don't even say b naught. It's x of t naught. Tangent line to sometime t naught is evaluate where you're at on the curve. There's the vector that dictates the direction you were going. This is what gives you the line. The picture here looks like this. That point is x of t naught. It has some vector sticking out of it. That's the velocity vector called x prime of t naught. And if you continue that line in both directions, you get the tangent line. The physical interpretation of this, because we're finally in the land of physical interpretations, is if there was a force that was bending this object and all of a sudden that force ceased to exist, what the derivative describes is what the object would continue doing in the absence of any other force. Okay? This is sort of like intrinsic to Newton's laws. So we'll compute one of these, and then next time we'll start building up a picture where we're actually going to be able to use the vector math that we know already, essentially just a whole bunch of vector derivatives and cross products to show that planets have to like sit in a plane. Okay, so we got to be careful here. In a system consisting of one planet and one sun, the planet must orbit in a plane. The n-body problem in physics is actually incredibly computationally difficult. Even the three-body problem is not solved completely. So Kepler made a massive simplification by assuming one planet and one sun, but it's close enough. And this is basically the picture that we're going to be using. It's just these sorts of computations. Vector derivatives and approximations using cross product. So how easy is this to do in practice? Find a tangent line. Let's see if we make this simpler. Find x prime of t for x of t is equal to 3t squared, t plus t squared, 2. Just to remind you, when you're computing derivatives of vector valued functions in one variable, you just take derivatives of all the bits. If you wanted to compute a tangent line at a particular point, so if you want to compute the tangent line at t is equal to 1, you need to know x of 1, which is 3, 2, 2. You need to know x prime of 1, which is 6, 3, 0. And then you write down L of t is equal to the position, the direction, times how far away you got from 0. That anchors you at time is equal to 1. It's the center of your approximation. This variation t lets you sort of wiggle an approximation on both sides of the line, right? There you are at 1. If you let t be equal to 0.9, that says move slightly backwards on the line. T is equal to 1.1, we move you forward on the line. Okay? Same sort of typical tangent approximation that we've been doing. How fast is a particle moving at t is equal to 1?
Well, speed is the magnitude of velocity.
Speed is the magnitude of the velocity vector, which is the
So magnitude of velocity into speed. Okay, and so eventually what we're going to do is we're going to talk about how we can use these ideas, not just to, so we'll do Kepler's laws as a demonstration. And then we're going to talk about something called a Frenet frame. You've seen that in an earlier class. So a Frenet frame is a way of describing if you have an article traveling through space along some curve, it's subject to three forces. There's a force that makes it turn, so flat turns, that's related to curvature. Then there's something twisting it, so that's torsion or torque comes from the twisting on the path. And then you have like sort of forces that are pitching it up and down, right? And so any sort of description of an article of an object traveling on a three-dimensional path
can be thought of in terms of these vectors that describe its motion. And this is why this is at the core of mechanics. All right, so I'll see you guys next time. We'll talk about Kepler's laws, and I will post. I apologize for like burying that in the modules. It won't happen again without at least an announcement. I will let you know as soon as I know what's going on with the test, and keep it up. Thanks for your work so far in here. I appreciate it.